Hey guys, my name is Gabe Graves and today we go over Lab 3. So the main purpose of this lab was given a star of known mass that follows a known trajectory key to my email address to find the mass of the black hole it is orbiting. Additionally, some other purposes would be to use computational modeling to estimate real-life phenomena that cannot be readily recorded experimentally. And it should also be noted that the two main equations used in this lab would be Newton's second law and Newton's universal law of gravitation. Some other important equations, though, would be that the net force is equal to the parallel force vector plus the perpendicular force vector, as well as that, of course, momentum is equal to mass times velocity. So here are my key data points. I will mainly just be going over the data points, though, that I actually got numerical answers for. So for the first one, net force is equal to the change momentum. This is a very key point and will be used kind of down the road. So from this is the magnitude that I got for it. My parallel change in momentum I got by multiplying the change in momentum times the unit vector, and this is the magnitude I got for that. For my change in perpendicular momentum, I got it just by subtracting my change in momentum minus my change in parallel momentum, and this is kind of just how mentioned earlier where net force is perpendicular plus parallel. For the mass of my black hole, I got it by taking the magnitude of my net force times the magnitude of my star's position squared, and dividing it by the universal gravitational constant times the mass of the star, which we know to be 2 times 10 to the 30 kilograms. And then for this, the average I got was 8.66 times 10 to the 33 kilograms. So here's my GlowScript code used for initial conditions. You can see I use a gravitational constant of 6.7 times 10 negative 11. The change in time was 1 Earth day in seconds, and these values right here are used to calculate the average black hole mass. So here's my GlowScript code that I use for the while loop. Some of the main points, so this is just showing you how I actually first calculated my P final, P initial, and then eventually finding the change in momentum, so P final minus P initial, uh, and then also change in velocity, but then eventually that turned into actually finding the change in momentum over time. So that is just the change in momentum over change in time, and it should be noted that the net force is equal to that. And then additionally, I then used my P initial and the magnitude of my P initial to find my, I guess you could say, unit vector for momentum. And then I use that to actually find my change in momentum in the parallel, which is just the magnitude of the change in momentum times the unit vector. And eventually my change in momentum in the perpendicular, which I just, again, used final, or my overall total minus my parallel to get the perpendicular. So here's how I actually calculated the mass of my black hole. So as you can see here, Rmag, or the magnitude of the distance between the star and the black hole, is just the magnitude of the star's position. The mass of my black hole is just the equation that I had said earlier. And then these two values are actually used to find my average black hole mass, where the sum of the black hole is just going to be plus equal to the mass of the black hole, and the count is plus equal to 1. So in the end, it's just going to take the overall sum of these and divide it by the number of sums that it took. This is just used to update the current position velocity, and then it should be noted that I also eventually then print out the average black hole mass towards the end. So here's just the video of my GlowScript model. So as you can see here, the orange force vector is going to be the net force, the purple is the parallel, and the blue is the perpendicular. So what does it all mean? So we know that Newton's second law states that the force is equal to the change in momentum. Therefore, the net force and its parallel and perpendicular components must be equal to the change in momentum and its parallel perpendicular components respectively. This is also shown through these equations down here, where for the parallel component, it's going to be equal to the change in momentum over change in time times the unit vector, as it is in the direction of motion. And for the perpendicular component, it is going to be equal to the absolute value of the momentum times actually the change of the unit vector, or the unit vector of momentum over time. So what if the original black hole was replaced by a new black hole and the star's motion remained unchanged? Well, then this would mean actually that the new black hole would have the same mass of the original black hole. This is because actually if the new black hole did have a different mass than the original, then this would overall then affect the net force that the star feels, which would then affect its acceleration and overall affect the motion of the star as it orbited the black hole. So some possible sources of error would be mathematical error, such as when setting up the function. And then also the model assumes that the mass of the two objects stays the same, as well as that the black hole does not have an accretion disk. So basically it's just that this is just a very simple model to sort of estimate the mass of a black hole computationally. Thank you.